Hello and welcome to this lecture on topological quantum field theory. This will be the first lecture from a series of lectures on topological quantum field theories. Today I'll give a brief introduction into the works that motivated TQFT. We'll talk about briefly about cobordisms and the functorial approach to quantum field theory. And finally I will talk a bit about invariance for the manifolds that we will be studying and how quantum field theory can give us a way of constructing such invariants. The next few lectures then will be on categorical aspects of topological quantum field theory. Specifically, I will introduce some ideas in category theory, including monoidal categories and categorification. And I will go over Feynman diagrams, cobordisms, and other ideas in the future. So let's start with the introduction. So 1, introduction. Also note that I will be using a variety of resources. I will have in each lecture I will have them in the description, so you can find them. The first few lectures will be based on Bruce Berlet's master thesis titled Categorical Aspects of TQFT. Now, let's start with an introduction. What exactly is TQFT and how did it start? So, topological quantum field theory is the study of theories on manifolds that are topologically invariant. So we have an action that does not depend on the metric. This subsequently generates, as just mentioned, topological invariants, which we can use to study the manifolds. Now, the probably most famous example of TQFT is also the one that marked the beginning of TQFT, and it was Witten's work in 1989. So Witten, 1989. Michael Atiyah, a few years earlier, had proposed to physicists that they should work on a way of expressing a Jones polynomial in terms of quantum field theory in models, three-dimensional quantum field theory models. And Witten did exactly that. What he used is this thing called the Chern-Simons action, the Chern-Simons 3 form to be more specific, was used to construct a field theory on S3 that has some properties that allow a three-dimensional interpretation of the Jones polynomial. It was the first, back then it was the only a manifestly three-dimensional interpretation of the Jones polynomial. The Jones polynomial is a Laurent, it's an invariant and not invariant. I will talk about knot theory much more in the future. So it's a Laurent polynomial that discriminates between different types of knots. So for example, the unknot, or if you have a trefoil, let me see if I can draw a trefoil. Can never really quite get it. Let's see, so this goes over here. Nope, it does not. I should go over this, so. Well, that's not correct, is it? 1 second, I'll get it. This is our trefoil, and it helps with discriminating between, for example, the unknot, the trefoil, and a higher crossing number knots, and different knots of the same crossing number. And what he did is he expressed this polynomial as the holonomy in Chern-Simons theory. I will have a lecture series on gauge theory, which I would recommend you watch if you're fuzzy on these things. This will be released a bit later on, like at the same time as I'm releasing this series. So if you're still not comfortable with gauge theory, I would recommend you perhaps read a book I will have in the link in the description for this. It's by Munyan and Baez, titled Gauge Fields, Gauge Theory, Fields, and Gravity, Knots and Gravity. Really good book. Definitely recommend it. So he found a connection between, well, as I said, Chern-Simons theory and Jones polynomial. Well, on S3. So let's be a bit more precise. What he said is that the Jones polynomial, so J of k, is precisely given by the expectation value of the holonomy of our gauge field over our knot, around our knot. So mathematically, this is given to us by the following formula. Now here k is an integer, and it allows for roots of unity in the complex plane, which is it's an artifact of the Chern-Simons 3 form. I will talk more about this in the future, or once we've talked a bit about category theory, we'll come back to this. But if you're not very comfortable with this, I would recommend you read the book that I mentioned, which covers these things nicely. But this is a bit outside the scope. It's not within the scope of this lecture series. What I'm trying to get at is that the theory that I'm currently building is metric independent. So this thing here now is our action. This is our Jones polynomial, where here we have holonomy, or a Wilson loop of our gauge field around the knot k. So just a few words about the connection. This connection, it's the pullback of an SU2 valued connection we can choose the principal bundle to be trivial, right? Because we have a simple Lie group, which means that we will always have a globally defined section. So we can choose a trivial bundle, because why not? So this thing here, as I mentioned, has the interesting property that our action is independent of G. What does metric independence mean? Well, it's kind of obvious that metric independence implies diffeomorphism invariance. So this is exactly what makes a theory topological. Metric independence, topological. So from now on, I will use the word topological theory, or something is topological, to refer to the fact that it's metric independent. Okay, so now let's go a bit back to the path integral. Let's talk a bit about quantum field theory and build up to this metric independence and what it means. Specifically, let's try to create a more general way of thinking about quantum field theories. The most basic way is to construct a quantum field theory through canonical commutation and second quantization. But this is not really what we want to do here. We want to create invariants. And if you notice, this action here is metric independent, which means that it is a topological invariant over manifold. Also, keep in mind that it does the action itself depend on the connection, but the weighted sum over all these actions, over all gauge fields, is itself gauge independent, right? We don't discriminate over fields because we sum over all of them. So we can think of quantum field theories in terms of their path integral formulation, such that we can get a nice geometrical picture. So path integral is exactly this, which is a sum over all these exponentials of our action. And for our case, what we will be looking into, M is a three-manifold. Unless otherwise stated, we'll talk about a more general category in a bit. But for most part of this series, we will be focusing on three manifolds. So now, if SA is topological, then it follows that Z is a topological invariant of M. Is an invariant of M. And actually, this is a really good way of constructing invariants. We are able to consider quantum field theories over a specific manifold if we endow it with a connection. And if the action is topological, then we get a topological invariant. Let's make this a bit more, let's organize this a bit better in terms of, let's create a recipe. Let's create a recipe for invariants. So recipe for invariants given M. So we have our manifold M. So the first thing we need to do is to endow it with a connection, right? We want a field, we want a gauge field. Endow M with a connection. Now for the majority of these examples and introductory examples, I'll be using a very basic theory. So just with one connection, we won't have like fermions or any interactions or anything that can make our lives more complicated and lose sight of the big picture ideas behind TQFT. So we endow our space with a connection, then we compute the action, and finally weighted sum over all A's. But keep in mind that path integrals, they're not only computational machines, so they're not just this sum. This sum has a much more it has a much deeper meaning than just a sum or just a number. It says a lot about the underlying dynamics, and as we just saw, it also can give us a lot of information about the manifold on which we have our quantum field theory based on. So this here is a nice way of thinking about quantum field theories, like the path integral approach. But we can make it a bit more natural and more geometrical by introducing the idea of cobordisms. So a cobordism is it's basically a larger manifold, let's say an n-dimensional manifold, that connects some closed n-1 manifolds. So let's see, cobordisms. What we have is, suppose we have just a three manifold M with boundaries sigma 1 and sigma 2, so the disjoint unions of sigma 1 and sigma 2. Then M is called our space-time, and sigma 1 and sigma 2 are our initial and final states that are given. So what this means is that we can think of our space-time and of our theory as the time evolution from sigma 1 to sigma 2. So This thing here is our initial state, and this here is our final state. So time moves like this. This is our time. And the splitting basically represents interactions. So this could, for example, be the decay, the pair creation, for example, and then proceeds to annihilate. So here inside we can have a lot of different interactions, but this right now is not very this is not the point right now, but you can have a lot of interactions. So we call M is a cobordism from sigma 1 to sigma 2. Now, how can we connect this to quantum field theory? Well, let's see, cobordisms in QFT. To each sigma, so to each state, initial and final state, which in this case is a 2D closed manifold, we associate a Hilbert space. Which I'll call fancy H, well, as fancy as I can do it, sigma, which is the space of fields living in S, living on S. So this gives the very basic Schrödinger picture idea, where we have some physical state psi that is a functional of our space fields. Why a functional? Well, since we are talking about path integrals, we want to insert our states or our observables in our partition function and compute the correlation functions. So we effectively want something that we can sum, that depends on the fields in a way that we can sum over all of the fields, such that the physical result does not depend on the gauge field. We don't want to have any gauge dependence, because we want a physical state, right? So we get the basic Schrödinger picture, where if A is some state, then psi of A just represents amplitude of finding psi in A. Now this has a very, very trivial basis, like AS has a very natural basis, which is precisely the delta functionals. So if we have like A hat and A hat prime, this is just a delta function of these here. So this is all nice, but we're still missing a crucial part of quantum field theory. And that is precisely how we evolve over time. So like how do we evolve from one state to another? Now, using this, we can expand psi as a superposition of those. We can have a spectral decomposition, and we can all express this as a superposition over our bases. And now, what we can do is that the amplitude of a system in A1, so like in state A1, in sigma 1, the probability of it being found, let me actually make them subscripts, it's easier to understand. The probability of it to be found in a state A2 in sigma 2 is given precisely by this path integral. So we have the initial condition we said is A1, and at sigma 2, this is just A2, and this is an exponential. So this is basically the fundamental formula for quantum field theory. This gives us a definition of the time evolution operator, which is associated to our cobordism, to our cobordism M. So U, M, is the time evolution operator. Time evolution operator. Now we can start being a bit more precise and see how to every space-like manifold sigma we associate some Hilbert space, a Hilbert space, and to each cobordism from S1 to S2, we associate a time evolution operator. U of M. So now what this means is that we effectively have constructed the definition of a TQFT that Antia gave, a QFT. So let's write this down because this is very interesting and cool. It is a functor from the category of n cobordisms to the category of Hilbert spaces. So actually, let me just write this more precisely. And this is precisely this functional perspective on quantum field theory. So we have that Z is a functor from n cob to Hilb. We will talk about this category in the second lecture more, see what the morphisms are and what it looks like. But, well, to be more precise and give credit where credit is due, this was first pointed out in a paper titled The Definition of a Conformal Field Theory by Segal, and it has shaped the way we look at quantum field theories. Now let's give some example in four-dimensional theory. Right now, keep in mind that we have not talked about TQFTs yet. Everything we've talked about thus far right now is mostly related to quantum field theories. It's in general. We haven't really talked about any topological things right now other than the Chern-Simons. So if we take, for example, 5-4 theory, then we have that sigma t, for example, is just a time splice, so t, and our cobordism from T1 to T2, so basically the trajectory from two specific points in time of how, not the trajectory, but how the evolution of our space is just R3 x T1 T2. So this is a four-dimensional manifold with these boundaries T1 and T2, and we have our space-like manifolds sigma t1 and sigma t2 representing the space. Now, again, this is nothing topological, but this is just here an example of how we can think of this time evolution. But here in 5.4 we have flat space-time, and there is nothing really interesting, there's nothing really cool that happens. So where is topology? Well, topology comes from our observables. We want TQFT, well, not exactly the observables, but the metric independence that the correlation functions enjoy. So we have correlation functions that are topological. So if we have, for example, O1, O2, On, which are just observables, so functions from space to complex numbers, then the correlation function of this product is just this typical expression that we have for the path from the path integral formulation. But this thing here is metric independent. Metric independent. What exactly does metric independence look physically, and what do all of these things look more pictorially? So metric independence basically means that we have diffeomorphism invariance. We have, let me write this down, metric independence implies diffeomorphism invariance. Okay, so this wraps up this first lecture on topological quantum field theories. The next lecture will be on categories, cobordisms, and Feynman diagrams. Hope you've enjoyed this, and I'd be open to answering any questions you want to leave in the comment section. Thank you for watching.